Hi, y'all. Welcome to a round of engineering. And yeah, let's just get started. As the syllabus would suggest, this week we are going to discuss not circuits, but actually a branch of mathematics that's referred to as linear algebra. Linear algebra. Algebra. And just to give you kind of where does the name come from, linear algebra studies the behavior of equations, which can be written as a linear combination of variables. So if I write down a linear equation, you can probably come up with one on your own. Yeah, something like y is equal to mx plus b. Mx plus b. This would be a type of linear equation, namely because each of the variables, the y and the x, those tend to be the two unknowns, if you will, those are both raised to the first power. And so that's the linearity of it. Now, of course, you can have more than one independent variable. So linear algebra will tend to write equations more like this. They'll say y is equal to, now we'll have a constant 1 times the first the first independent variable plus some constant 2 times the second independent variable plus, and we'll keep going, dot, dot, dot. And notice I've written this. This is still considered a linear equation. There are no quadratics or square roots or things raised to the third power. And so usually we'll see this. Of course, this is kind of sloppy. Sometimes you'll see it written as this: the summation from I equals 1 to n of, we'll say, our constant I times xi. And then we'll just use the index I to represent which independent variable. Do I mean x1? Do I mean x2? Et cetera, et cetera. Now that in itself is sort of, I don't know, blasé, boring. Okay? But there's more. Of course there is. Okay? Linear algebra tends to look at not a single linear equation, you guessed it, a system of linear equations. So I've written one here, but say, for example, there is a second equation that I can write. So I'll call this one y1. Perhaps there's two equations that you want to simultaneously solve. So I have a second variable, which I'll call y2, second dependent variable, and it can also be written as the summation, we'll say from I equals 1 to n, of some different constant. So instead of c, maybe I'll use, I don't know, I'll do the reverse alphabet. I'll call it b. Some different constant, bi, times our independent variables. So I'll leave these x's the same, right? These are our independent variables, so those x's will stay the same. And linear algebra will say two things. It will first of all determine whether there is a common solution for both equations. And if so, what is that solution? Hopefully you can appreciate this can get sort of difficult really quickly. Now, of course, you don't have to stop there. You could have, instead of just two equations, you could have 5 equations or 10 equations. Okay. So that's one of the questions that linear algebra works to try to understand is, does a solution exist? So does solution exist? And if so, what is the solution? Now here's, zone in for a second. I know that's kind of a little bit of an introduction, a bit of theory, that kind of thing. Zone in for a second. Here you go. Right? In this course, we are going to use linear algebra. Okay? We're going to need it in order to find solutions to a system of equations. So the reason I'm presenting this mathematical concept right now is because as we start in our class, say next week even, we are going to apply some of these ideas of linear algebra to find solutions. And I'll say that it will make your life easier. This is a way for us to speed up the sub and solve process, which you're probably already familiar with. I have 10 equations. I need to sub and solve to find the variables. This will speed that up. That's why I'm introducing it here. Okay? So I'm trying to make your life easier. The upshot on this, okay? Mathematicians really care about figuring out if a solution exists. Okay? Physicists, for the situations that we will be dealing with, we know that the solution exists. Okay? And how do I say that? Well, the system of equations that we will generate are going to be based off of an electronic circuit. Can you build the electronic circuit? Yes. Okay. The system of equations that we will generate are based on an electronic circuit which we can build. Therefore, a solution must exist. I can build the circuit. Okay. So we are not going to concern ourselves with this first piece. Does a solution exist? Okay. That is not what we will concern ourselves with. If you're interested, I believe you will cover some of this material in Phys 245. If you don't cover it there and you're really jazzed, there are standalone linear algebra classes here at the college. I would have to look up the catalog codes. Okay. So let's go ahead. Let's talk about, I'll first of all go through and talk about how do we find a solution. Okay? And we'll do it from a graphical standpoint, number one, and we'll run through it algebraically as well. So let's go ahead. Let's get an idea about how do we find solutions to linear equations. And I'll do it in the context of a specific example. So here's our example. Let's say for a moment we're dealing with this equation. It will be, we'll say, here's one linear equation. We'll say negative 2x plus 5. So I'm going with one dependent variable and one independent variable. And the second one, why don't we go something like y is equal to 5x plus 2. And even though we don't bother ourselves with this, you should probably, we're not going to go through and formally prove it. But if I look at this equation for a moment, does a solution actually exist? And don't do algebra. Look at the equation and tell me, does a solution exist, and how do you know that a solution exists? Or why not? Hopefully you see it. Okay? Look right here. Look right here. I'll outline it in yellow, which is probably a terrible color. Look right there. I have circled the coefficients of the independent variable. Okay. That would be the slope. And so this one represents a line of slope -2. This bottom equation represents a line of slope 5. And the real question is, when I say, does a solution exist, the question becomes, do the two lines intersect? And survey says, yes, because they have different slopes, these two lines must intersect somewhere in space. Therefore, a solution exists. Right? That intersection point is the one location that the x and y values match, and therefore that's the answer. In fact, graphically, we can do that. Okay. Let's pull up Desmos. This is a perfectly valid a way of going about it. Let's go ahead and pull up desmos.com. So I'll go ahead. We'll pull it up right here on the screen. Let me stretch it out just a little bit so we can see it. Okay. And we'll go ahead and type this in, negative 2x plus 5. Okay, so we have our y-intercept, and we have our negative slope. And then we can do something like 5x plus 2. Okay. And boom, right away, we see that we have a point where the two lines intersect, and we can click on it. We can actually find that this point, oops, excuse me, I've lost my 0.42, 4.1. So we'll say that x equals 0.42 and y equals 4.1. I think there's a 4 here. So we have graphically solved this system of equations. Boom, you're done. Pretty cool, huh? Of course, if we wanted to do it algebraically, generally the process would be something like sub and solve. I will take the top equation and solve for x, then plug it into the bottom equation. So this was graphically. And then we have algebraically. And of course, you don't need me to do this, but I'll run through it, but you're probably already well ahead of me. Right? Go ahead, finish it, but I will do it as well. So take a minute, pause, okay. Find the answer. And while you're finding the answer, I will go ahead and find the answer as well. And then we will confirm that the two answers match. So the first equation, I get something like this for x, and now I will sub it into the second equation, 5x plus 2. So I get y is equal to 5 times y minus 5 over 2 plus 2. So now we have to get y by itself. And I'll go ahead and find a common denominator, so I've moved that, okay? And we gotta get it to the other side. So we have something like 7 halves. Y is equal to 29 halves. And that we see that y is something like 29 divided by 7. Okay. We can buy it. We see that it's slightly greater than 4. Of course, we're not done yet. Right? Oh, but wait, there's more. We have to back sub. Now that we have the value of y, we will want to sub back in. So I'll come back up here. We need to sub back in to get our value of x. So we have something like 29 over negative 14. And that's y, and then we have minus 5 and the minus 2. So we have plus, and I'll go ahead and multiply everything by 7. So I get 35, if I could write, we get 35 divided by 14. There we go, equals x. So again, we have this negative 29 over 14, and then we have plus 35 over 14. So we go ahead and work our little magic, and we get something like 6 over 14 equals x. You can see that's a little less than half, or 3/7. And boom. No surprise there. Now I'll highlight something for you. Notice how quickly we were able to get the answer graphically as compared to algebraically. Right? Graphically, we just typed it in. It took all of 2 minutes. And half that time was waiting for the internet browser to load. The downside to that is that there is no way for me to look at the 2 numbers that I got, that I obtained, and know the closed form expression. What I mean to say is there is no way for you to look at 4.14 and know that it's actually 29/7. Right? Graphically, you are doing a numeric approximation. So the upshot to graphically is it tends to be a little bit faster. The downside is that the answer is not necessarily obvious. You get a numeric approximation rather than the exact solution. The converse would be algebraically, it takes us a little longer to get the answer, but once we have it, it's exact. We know that's 29/7. So there's trade-offs there. Okay. And you could probably come up with another trade-off. You ready for it? Yeah, let me give you another example. Okay. And this is the reason why we developed the linear algebra. You say, well, why can't I always use the graphical method? And I'd say, have at it. Okay? If you always want to use the graphical method, okay, good luck. Let me give you another example. Instead of doing a system of 2 equations, you notice we had 2 equations, we had 2 variables, the dependent variable and the independent variable. Let's go ahead and do another example. Okay? And here you go. Let's do 2 independent variables and a dependent variable. Okay? In other words, I'll give you 3 here. We'll say, let's start off with y is equal to 2x1 plus 3x2 plus 1. And we'll go ahead and write down 2 more here. We'll say negative 4x1 plus 2x2. Okay. And the last one we'll say is y is equal to, we'll just call it x1 plus x2. And we'll throw in a minus sign there. Okay. Now, please keep in mind, x1 and x2, these just represent independent variables. And y is the dependent variable. Just to remind you. So there's actually 3 variables here, which is why I've written down 3 equations. Now, you can go ahead. Of course, we can do the sub and solve. Okay. Let me show you how to do this graphically, and hopefully that will highlight why it's going to be a problem in the future. Okay. You could probably already see it, actually. Let me ask you this. How many dimensions do I need to graph in order to come up with the solution? Three. If I have 3 variables, right, I have 2 independent variables and a dependent variable, what does that mean? That means that I need to have an axis for the values of x1. I need to have an axis for the values of x2. And I need to have an axis for the dependent variable, what I called y. So inherently, if I want to use the graphical method to solve this system of equations, I have to do it in 3D space. One for x1, one axis for x2, and then one axis for the final dependent variable. Okay. Let me go ahead and show you how to do that. Okay. And we'll approximate the solution. Okay. Now, unfortunately, Desmos doesn't do this for us. we have to do something stronger. And so I'm going to open up MATLAB and show you a little bit of kind of key functionalities. This is more of a familiarization, but I want you to know that you can do it and start introducing you to how. Okay, so give me a minute. Let me pull up MATLAB. Okay, thanks for your patience there. So on the screen, I have MATLAB loaded. Okay, and I don't know if you should hopefully start gaining some familiarity with MATLAB. If you haven't already, MATLAB is available to you for free through the college. Okay, so I'll see if I can post the link. There you go. Magic of internet. Okay. So you should be able to click on this link. It will take you to the Hanover College license page. You use your regular Hanover email or your Hanover ID and your password, like your email ID and password. And that should log you in and give you the option of downloading MATLAB. Okay. For those of you that are unfamiliar, this top section is the editor. So I tend to save things as scripts. And so I use the editor so that it can save a series of commands so that I don't have to regenerate them later. Okay. So say you're doing some sort of complicated analysis and you don't want to have to record everything you did. You want to save the command structure. That's what you can do here. Okay. On the bottom, this command window, that's where those commands that you write in the editor are executed. So you can think of, okay, well, if I say x is equal to 1, so I want to create a variable x and set its value equal to 1. Okay. So if I do that in the editor and I hit run, you'll notice that it will spit it out in the command line. Excuse me, I have to save it first. So first time, okay, sure. Oh, excuse me, I've already got that open. Let's try that again. So you notice when I hit run, it spits out in the command line. It says what is being executed, which script, and then it prints x equals 1. Now that's the second thing. So it takes the command that I've written in the editor and it outputs it to the command window. So I can execute a series of commands, say y equals 2, z equals 3. Excuse me. And if I hit run, now you see that it says x equals 1, y equals 2, z equals 3. In addition to that, once those variables have been created and stored, I'll look over here on the right-hand side and we have what's called the workspace window. What that is it's telling you what variables are and what their values are. Now we can extend it to larger ideas, but we'll leave it there for right now. Okay. What I would like to do is use this for plotting purposes. If you say, well, I don't want you to actually spit the commands out in the command window, I just want you to execute and be done. Okay. You can put semicolons behind each line. Then when you run, it will say in the command window, I ran your script, which mine is called untitled, and I have finished running it. So it doesn't give you all that feedback. If you want to clear up everything, if you want to get rid of all the stuff in your workspace, you can type what's called CLC. It's a command that MATLAB understands. I don't remember what it stands for. You hit enter, it'll clear your workspace, or excuse me, your command window. You want to clear your workspace? Clear. And now you'll notice on the right-hand side of the screen, when I hit enter, I've lost everything. Be very careful with CLC or clear and CLC. Make sure you know that you want to do it. So let me walk you through. Well, let's go ahead and plot in 3 dimensions right now. Okay. So the first thing I want to do is I don't want to assign a specific value to x. I want to have it as a symbolic variable. So what I'll call it, there's a command, it's called sim. So symbolic variable. And I'll call it x1, and I call the other one x2. So I'll leave those like that. Declare a couple of symbolic variables. And when in doubt, you can always hit run just to make sure everything works fine. Okay. Okay. And then you can always comment it later. That's usually how I do it, is I write a couple lines, I execute to make sure everything's fine write a couple lines. So that's the first thing. I want to declare these as symbolic variables. In other words, I want the MATLAB to recognize that these represent numbers, but they don't have a specific value. Now here's the next thing. And this is something you're probably not as familiar with. I would like to declare a function using those symbolic values. So I'll call one of the functions f. I guess I could call it y1. Let's call it y1, the first function. And so I want to declare it as a function. So there's my variable name, y1. I'm going to put the equal sign, the assignment operator. So everything that follows the equal sign that's what gets assigned to the variable y1. Now here's the part. I mean, I want to do something like 2 times x1 plus 3 times x2 plus 1. Okay. That's the function that I would like to type in. The thing is I have to tell MATLAB that I'm using these symbolic variables. It doesn't understand what x1 and x2 are because I haven't told it to use the symbolic variables. So I'm going to put a small thing in here, x1, x2. This is telling MATLAB now, hey, these symbolic variables that have been declared, I want you to create a new variable called y1, the dependent variable. It is a function of the 2 independent variables, and the actual equation is given by this. So let's go ahead and hit run. And you notice now we have a new variable in our workspace called y1. Now say, for example, you want to evaluate a particular point. I'm in the command window down here. Now that I have created my function y1, I could put in something like actual values for x1 and x2. And you'll notice that it'll go through and calculate it out for you. Pretty cool, huh? Or if I put y1, 0, 0. So I want to evaluate it at x1 is equal to 0 and x2 is equal to 0. Okay. But wait, that's not where we're going. We want to be able to plot this thing. Okay. So let's go ahead now and get an idea about plotting it. Now, if you're familiar with MATLAB or you've played around with some of the plotting, there are, of course, scatter plots and bar graphs and pie charts. What I would like to do is a surface plot. Since I have 3 variables, I need a 3D surface. So usually the command is something like surf. You can usually take a stab at what it is. So I want something like surf, and I want, now here comes the first thing, I need to give it its function. So I'll call it y1 and closed it. That's fine. In fact, we'll do that first. Now, the only other thing is because y1 is a function, not specific set of values, I'm going to have to put an f in here. What this means is I want to plot a function as a surface. Let's go ahead and run it, see what happens. And we should have a plot window. Boom, there we go. So what we're looking at now is on one axis, the value of x1 running from -5 to 5. We have our value of x2 running from -5 to 5. And then our third axis is the value of our function. So that's just one. And of course, again, because of the linearity, we actually end up with a flat plane through space. Each of these represents a plane. So I'm going to throw in a couple of extra things in here. I'm going to call this one, I'm going to set edge color equal to red, okay? Because I'm going to plot 3 of these, so I want to be able to kind of visually see what each one is. And then I'm going to call the rest of the plane, I'm going to color it pink. So let's go ahead and run that and we'll just see what the result is. So now I have the edge color as red, so the squares have boundaries of red, and you notice that the plane itself fades from black to white through shades of pink. That again is not necessary. I think it just helps visualize the 3 planes. Go ahead, take a minute. I want you to create 2 more functions. Okay? We'll call it y2 equals, and we'll call it y3. Okay? Go ahead, take a minute and write down what those equations look like, number 1. And the second one is go ahead and write down the surface commands. So if you want to actually fsurf, go ahead and write down the 3 plotting commands. You got it? Good, 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 good. Here we go. So again, I need to tell MATLAB that y2 is a function of the 2 independent variables. And then I have to tell it what the functional relationship actually is. Don't forget the negative signs. Or the negative signs, and don't forget the multiplication signs. If you write just 4x1, it interprets that as a variable called 4x1. MATLAB is not smart enough to understand implicit multiplication. So you have to write the multiplication signs in or the parentheses. Okay. Then we have 2 times x2, and we're done. And we'll repeat the same thing for the third one, keeping track of what our equations are. So we have something like x1 plus x2 minus 2. Sweet, huh? Well, let's go ahead, and I will go ahead and write down one of these. We'll call it y2, and I'm going to set the edge color. Let's go ahead and set it red, green, blue. So I'll call that one green. And you'll notice an issue now if you go ahead and plot these. Oh, excuse me. Oh, fat finger typo. Excuse me. There we go. That wasn't the thing that I expected. Okay, here we go. Now we go ahead and run. How about we put a plus sign in there? 2 times. Hey, we all make mistakes. Here we go. Okay, now we're ready. Let's go ahead and run it. And you notice something. Which one is actually being plotted? The second function, right? The problem is I want to show both plots on the same graph. Okay. What MATLAB does is that it plots this one. Okay. Then it sees a second plotting command. It gets rid of the first plot and plots the second one. Okay. So what we want to do is tell MATLAB, don't get rid of the first plot. So I'm going to put it's a command, it's called hold on. What this means is that after you do the first plot, save that, continue to display it, and display the second plot on top. So that's one way of actually plotting 2 things. Let me go ahead now and let's execute. Ah, there we go. Now you see why I said, okay, I'll call one red and I'll call one green. Okay. And what we have now are our 2 functions. And you notice that it doesn't intersect at a single point in space, but rather a line. The intersection of 2 planes in space is a line. So this is, and you can click and drag, you can kind of rotate to see what's going on here. But you can see that there is this well-defined line in space where those 2 planes intersect. Now, of course, we want to plot our third one. So let's go ahead. And you say, well, Greg, surely there's going to be some place where this line in space intersects the third surface. You say, oh, nay, nay. That's not necessarily true. I've defined my line in space. What happens if this third function just happens to be parallel to that line? Okay. So it's the same idea. Same idea as the 2 variable equation. It's just that now it's a line and a plane that could potentially be parallel to each other. Well, let's go ahead and throw in our third command here. if I can type y3 edge color blue. There we go. Run that sucker and pull up the final plot. Ah, good, 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 good. So we see immediately that the blue plane is not parallel to the line that intersects the red and the green. And so again, we can kind of finagle our way around. We see where that intersection point is, somewhere right here in the middle. Or if you go from the top-down approach, you can see where the intersection of all three colors, that would be the value of x and y, excuse me, x1 and x2 and y that satisfies this equation. Let's go ahead and zoom in. Okay, so all I've done is I've hit the magnifying glass, and you can click, and you notice that the scaling on the horizontal and vertical axis is changing. So what we're doing is zooming in here. You can see it is changing a little bit. Okay. And at some point, we're going to just want to click on that intersection. So we get a choice. I can go there, I can go there. Let's click on this one. And what do we get? We get a final value. Excuse me, let me write this down, and then I'll put it on our PowerPoint. We see that we get a final value of x1 is equal to 0.091. We get x2 is equal to negative 1.55. And we get that y is equal to negative 3.46. Right? Cool, huh? So let's we'll go back home, so you can hit the home button. And the same thing, if you want to keep kind of examining and rotating, you can kind of get a feel for where these three planes intersect. Keeping in mind, you're not guaranteed necessarily that they all intersect at the same location. Now, hopefully you see the problem with the graphical approach. Number one, it takes a little while to do it. And number two, if you have more than two independent variables, you can no longer use this technique, right? Because we can't see in higher than 3 dimensions. You can't plot something in 4 dimensions or 6 dimensions. Can't do it. You have to do it algebraically. Sorry, don't kill the messenger. Okay, so we'll leave it there. We'll leave it at that. Let me close that out. Okay. And we'll return back to the comments at hand. Okay. So we found that x1 is something like 0.091. We found that x2 is something like negative 1.55. Excuse me, I should have obeyed sig figs. Get rid of the 1 there. There we go. And we get something like y is equal to negative 3.46. Now, algebraically, I know you know how to hammer through this. Okay, sub and solve and go through the whole thing. Okay. We won't do that. I encourage you to practice that at home. Go ahead and try it for another time. Okay. What we can do, though, is we can say, are these the correct answers to this set of equations? How do we know? So you can go ahead and sub and solve, take these answers, and double check that they actually work in these equations. Good sanity check. So we'll do 1. So let's ask ourselves, let's do the top one here. We'll say, is negative 3.46 equal to, question mark, 2 times 0.09, so there's an extra 0 in there, okay, plus 3 times negative 1.55 plus 1. So 3 times 1.55, so 3 times 1.5 is 4.5. plus another 0.15. So this would be something like negative 4.65 plus 1. And this is 0.18. And now you can see, yeah, that's I mean, I'm rounding, of course. Okay, so I truncated these digits right here. Okay. But you can kind of see, okay, well, 0.18 plus 0.465, that'll give me something like negative 4.5. I've jumped ahead there. This will give me something like 4.5, and then I add 1 to it. So yeah, okay, that's roughly negative 3.46. Right? This is negative 3.5. So that does work. Yeah. So that's the first thing. I'll say you can do it graphically. It's faster sometimes, but it's limited to from higher dimensions. So that's why we have to develop algebraic techniques in order to solve these equations. Okay? And I'll say faster than just sub and solve. We've all suffered through sub and solve. We all hate it. We wish there were a better way. There is. That better way I'll leave for next lecture. Okay? So kind of get your mind wrapped around what's going on here. It's a good first introduction. Play around with MATLAB a little bit. If you need some revision on matrix multiplication, tune in to the next video, the matrix multiplication one. And then after that, we'll actually start developing ideas of how to solve this system of equations faster. Thanks for your attention. I'll see you next time.